Let's continue our discussion. We just talked about Newtonian fluid, and now let's see how non-Newtonian fluid behaves. By definition, non-Newtonian fluid is any fluid that isn't Newtonian. So let's just recap what we just discussed. For Newtonian, we have shear stress being proportional to shear rate. Specifically, we say tau equals to mu gamma dot, and the gamma dot is the shear rate. So we have shear stress and the shear rate. A straight line means Newtonian. Any fluid that deviates from a straight line on the tau versus gamma dot curve is a non-Newtonian fluid. So depending on the curve, you may have different types. For example, you may have a curve look like this, or a curve look like that. And the first type of this line, we just put 1. This is called dilatant fluid. The features is exhibits shear thickening behavior. Shear thickening. What it means is if you look at the Newtonian is as the gamma dot increase, as the shear rate increase, the shear stress increase proportionally, so it remains on a straight line. And for shear thickening fluid, as the gamma dot increase, the shear stress increases more than a linear fashion. So it means the shear stress getting larger and larger in a way that the fluid feels like it's thickening or become more viscous over time. So this is called shear thickening fluid. And these two, this line number 2, this is called pseudoplastic fluid. This is opposite to the dilatant fluid. And this type of behaviors, or this type of fluid behaves like shear thinning. So as gamma dot increases, although the viscous shear stress increase, however, it increases less than a linear fashion. So the effective or apparent fluid viscosity actually decreases as gamma dot increases. So you may wonder how do we describe the viscosity in non-Newtonian fluid? So for Newtonian fluid, we have a single physical quantity, we call it mu, we call the dynamic viscosity, it's unique. As you can see, for non-Newtonian fluid, depending on gamma dot, the viscosity can be different. So there is no one single viscosity can be used to describe non-Newtonian fluid. Instead, you have a list of viscosity that depends on gamma dot. So for a given gamma dot, you would have the corresponding viscosity. And those viscosity, sometimes you may be able to find it from a handbook or some charts if available. If you still would like to describe viscosity in some way, there is a quantity we call the apparent viscosity. Apparent. This is defined as tau divided by gamma dot at each gamma dot value. So that means for different gamma dot, you will get a different apparent viscosity. And this is just the nature of the non-Newtonian fluid. This is called apparent. So we need to be mindful that this apparent viscosity is not a constant. So not constant. It depends on the shear rate. Okay, so we have gone through the two popular type of non-Newtonian fluid, like shear thickening and shear thinning. There are some other types of fluid which are also popular, which we call the yield stress fluid. So let me draw one. The third one is an example of yield stress fluid. The yield stress means it requires a finite yield stress or a small stress to begin flowing. So here the stress, this amount is tau y. So tau y is the yield stress. So this is the minimum stress required for the flow to flow. Minimum for flow to happen. Below this threshold, the material behaves like a solid. Or material means the fluid behaves like a solid. The reason we mentioned the yield stress fluid in the context of this biotransport class is because blood is a yield stress fluid. So blood belongs to a Casson type fluid. So Casson type. Example, blood. It has a yield stress. It is related to the previous lecture, the previous lecture when we discussed the physical properties of blood because of the red blood cells. And let's draw it again. If you leave blood sample as non-agitated, and then you let it sit, then due to the gravity, those red blood cells would sit at the bottom of your glass, what your container, whatever you are looking at. And those are aggregated, and they don't like move easily if the stress on this block of like red blood cells is below the yield stress. So if the stress is less than the yield stress, then this chunk of red blood cells behave like a solid. It's not going to move. Only when your stress is larger than the yield stress, it starts to move. So in the blood vessel, when you see those red blood cells start to move within the blood, the red blood cells. If you see this move with the blood flow, it means the viscous shear stress within the blood is already larger than the yield stress. So this is all larger than O1, and it starts to flow. And the viscosity, when it's at a solid, it's very high. And the viscosity decreases as it starts to flow. And the higher the flow rate, the lower the viscosity. Of course, it plateaus. It cannot, the viscosity cannot like decrease to a zero number. That's impossible. So there will be a plateau, a minimal viscosity that the blood will displace. And we will discuss that in a different lecture. But right now, the purpose of this lecture is to introduce non-Newtonian fluid, specifically different types, and one type called yield stress fluid. This is what the blood behaves. You need a minimal stress to push this blood, to push these red blood cells, and in order to let it flow. Before we wrap up, let's look at a quick example. Let's see a pseudoplastic fluid under a shear rate of 100 per second experiences a shear stress 15 SF. What is the apparent viscosity at this shear rate? So for this problem, we will use the definition of apparent viscosity. To solve this, let's see the definition. Mu apparent equals to the shear stress at the corresponding shear rate. So this should happen at the same time. You cannot use shear stress for a different shear rate, otherwise it doesn't work. So now for this problem, when the shear stress is 15 Pascal, we know that the shear rate is 100 a second. So it gives us apparent viscosity 0.15 Pascal second.